Good morning. Ersin had a very nice introduction to transients, going into details for the neutron star transients, and I'm going to concentrate on the black hole transients and states, spectral states and state transitions um, in black hole transients. And most of what I'm going to talk about is, it's working. Uh, is from a recent review we wrote with John Thompson and Erin Kara, Black Holes, Timing and Spectral Properties and Evolution in the Handbook of X-ray and Gamma ray Astronomy. So if you are interested in this field, it has the most recent review of the X-ray and timing activity from galactic black holes. So this is the mandatory slide for all binary X-ray binary systems that you have seen it maybe more than a couple of times now. Ersin also showed it that we have a ordinary star, in this case a low mass star, accreting matter, in this case a true Rostov overflow, and then as Ünal mentioned in his talk, because of the conservation of angular momentum, an accretion disk forms, and at the center we have a compact object. If there's a neutron star, as Ersin mentioned, there is a surface, and matter then might emit from the surface in that case. But for the black holes, of course, there's no surface. There's the black hole event horizon, but the inner parts of the accretion disk is very hot, so you expect X-rays. And you could also see some other components here. Again, Ersin mentioned about these jets. There are also winds. So we have a couple of different types of outflows from these black hole binary systems. You might naively think that there's an incredibly large gravitational potential. It's like working like a giant vacuum cleaner. It's pulling everything towards the center. But in fact, black hole transient systems not only attract matter and accrete matter, they also power really high luminosity jets and very powerful outflows. So a lot of energy goes into the outflows as well. If the outflow is collimated, if it goes through a small volume with a small opening angle, we call it a jet. If the outflow is everywhere at very large angles, then we call it a disk wind. Okay, so black holes power outflows, both collimated and uncollimated. If we look at a black hole system with all the available telescopes that we have, that's the multi-wavelength analysis. There was a talk yesterday about this, which is extremely important to really understand all the physical processes going on in the accretion ejection environment of the black hole. We need to observe this black hole in all the spectrum of the electromagnetic, or all the frequencies of the electromagnetic spectrum. Basically, again, here we see the black hole, we see the accretion disk and the jet. And when you make such a measurement, collect data from the radio telescopes, near-infrared telescopes, optical telescopes, and then X-ray and gamma ray telescopes, you get something like this. Okay, this is called a spectral energy distribution, or SED for short. And here in the x-axis we have the energy, in y-axis we have the flux, energy times flux. It's the usual spectral representation. And these dots are all from different observatories. And you could also see this modeling, where you could see different components that make up this entire spectral energy distribution. And there are different components. Let's look at them one by one. Let's look at this component first. There is this solid line that goes almost flat, and then there's a break here, and then it goes down with a power law in energy, okay? This is a telltale signal of a compact conical jet, okay? I will come back to that later, but it is basically a combination of self-absorbed synchrotron radiation coming from the jet. Away from the black hole, we observe the jet in radio, as Ersin already mentioned. As you come closer and closer to the black hole, this jet spectrum emission kind of peaks at near infrared to optical, and then goes down in power law. And then some people claim that it all goes all the way to X-rays, but that's not confirmed. Goes down very quickly beyond near infrared radiation, near infrared bands, basically. The other things you could see is here, for example, there's a black body-like emission. So it could be the stellar companion or at the outer parts of the disk. So the inner parts of the disk is very hot. So it will emit X-rays. But the disk has a temperature structure. Again, Ünal talked about this. So the outer parts of the disk emits in near infrared to optical. All right. So then, of course, once you come to the inner part of the disk, we have the X-ray emission, which I will go into more detail in the next slide. We have the X-ray emission and the hard X-ray emission, which is perhaps coming from an additional component that we call a corona, which has an unknown geometry and a very high energy electron distribution that Compton upscatter soft seed photons from the accretion. So this is the general picture that we expect for the emission from all the way from the radio to gamma rays from a black hole binary system. As Ersin mentioned, these are transients. There is a website called Black Cat, which holds a census of black holes. Here in this graph, I show the light curves from the MAXI instrument that Ersin mentioned on the ISS. And I also showed the level of emission from the Crab Nebula. Crab Nebula, Tolga mentioned that, it was used to calibrate X-ray instruments. It's actually very bright. Crab is a very bright source. You could see that these black hole transients, they can be much, much brighter than Crab. In fact, some of the black hole sources, when they are in outburst, become the most intense X-ray sources in the sky. Okay, they become the brightest X-ray source in the entire sky. Okay. So most black holes are low mass X-ray binaries. The companion star is a regular star like ours, but we have also a few cases of high mass X-ray binaries. The most famous black hole, perhaps Cygnus X1, which was the first source to be claimed as a black hole, is in fact a high mass X-ray binary. Okay. You could see also from this light curves that black holes are quiescent most of the time. Their X-ray luminosity is below 10 to the 33 ergs per second. But then, as Ersin mentioned, we have these all sky monitors in the sky, MAXI, ASM, Swift, BAT, etc. And then when the mass accretion rate to the black hole increases, the luminosity increases rapidly. So we see these outbursts which are detected by these all sky monitors with this abrupt rise in the X-ray flux. And these outbursts, as I mentioned, that they can, we measure these black hole sources, their X-ray luminosities from 10 to the minus 5 Eddington luminosity to a few Eddington luminosity. So normally they shouldn't exceed Eddington luminosity theoretically, but some of them do. and there are certain reasons and explanations for that. But these Maxi J 1820, these sources are almost Eddington. They were as bright as they could be theoretically. Okay. So where is this brightness coming from in X-rays? So this is one representation of a possible geometry around a black hole system. Now, as I said, this is one representation because we actually do not know the exact geometry of this corona, a combination of very energetic electrons around the black hole, and it's actually one of the most sought information about the black hole. So one of the most important questions about the black hole binary research is what is the geometry of this corona. Here, this is called a sombrero geometry, where we have an accretion disk which is optically thick and geometrically thin, which is cut basically, and inside this accretion disk we have this very energetic 100 kiloelectron volt, hundreds of billions of degrees temperature electrons. Now, if you look at a typical black hole spectrum as shown here, you could see that it consists of a couple of, or actually at least three different components. The accretion disk has a temperature structure. It has a higher temperature on the inside and lower and lower temperature as you go out. So you have a combination of black body temperatures. Since this is optically thick, you have higher temperature black hole here, black body radiation here, lower temperature, etc. And then if you then combine all these black body temperatures, you get something called the disk black body model, a disk black body emission. So here in the soft X-rays, beyond a few kiloelectron volts, the X-ray spectrum has this component, the disk black body component, coming from the geometrically thin accretion disk. Now, the photons that originate from the disk, they enter this corona with all these electrons zipping around with very, very high energies, and they Compton upscatter. So there's Compton scattering, but now since the electron temperature or electron energies are greater than the energies of the photon, the scattering increases the energy. So what happens is that we have Compton upscattering, we have initial emission as a Comptonization emission from the black hole. Now, this Comptonization emission is usually with the form of a power law. Okay, so you could see that this power law emission is coming from the Comptonization. But of course, the electrons have a finite energy. Since they have a finite energy, they cannot upscatter these photons to larger than 3 times their average temperature. So we have this cutoff. So in the gamma ray regime, we have the cutoff in the spectrum, and this sort of a power law with the cutoff is a telltale sign of Compton scattering from very energetic electrons around the black hole. But we have a third component, because these Compton upscattered photons, already very energetic, 30 keV, 40 keV, they can hit back the disk, and they can interact in the disk. They can excite electrons in the disk. They can also downscatter. They can do Compton scattering in the disk as well. So then these excitations will create a bunch of lines, fluorescent emission lines, the most prominent being the iron line. Okay, so at 6.4 keV, we would see this iron line, but we would also see this Compton hump, this now downscattering of these energetic photons with the electrons inside the disk. So we have these few components: the disk blackbody component, the reflection component, and the quantization component, which we all use to understand the properties. Yes. Yes. So this is sort of unfortunate because this is Cygnus X1, which is a very complicated system, and then they had to use two black bodies to be able to completely. So it's kind of a complication when you have higher statistics. They are both coming from the disk, but that's only specific to this source. It's usually a single disk black body is enough to explain the emission from many black hole systems. Maybe I should switch to another source because it's causing some confusion there. Thank you. So as I said, the geometry of the corona is not known. Another explanation for the corona is that we already have a jet when the systems emit a lot of hard X-rays. We shall see that later. And it is theorized that this corona is basically the base of the jet. So it's coming from relatively smaller area where the jet is also starting from. And this is so-called lamppost model. So if you read papers on reflection studies with black hole systems, you might see this expression, lamppost model. It's not extremely physical in a sense that it is devised, it's created it's easier to do calculations if you have a point source at some distance from the black hole, and then you calculate, for example, general relativistic effects and how the iron line spectral shade changes. So it started with this idea, but then it got some attention and people started using these lamppost models to explain everything. But in fact, we shall see later that the polarization measurements, the recent polarization measurements with IXPE, shows that this is probably not the correct explanation. But nevertheless, these lamppost models are used especially to understand the shape of this iron line and where the inner edge of the accretion disk is. Okay. So I was just talking about this polarization measurement. This is a little bit complicated graph, but basically this is a very exciting result which recently came from the IXPE. On Wednesday, when I talked about polarization opening a new window on the X-ray sky, this is exactly what I meant, because we had competing explanations for the same spectral and timing properties for the geometry of the corona, but the polarization angle measured here is only consistent with a horizontally extended corona. So it could be like the sombrero shape that I showed you earlier, truncated disk, or some sort of a sandwich. It cannot be fully covering sandwich because of some energetic reasons, but basically the lamppost models, spherical lamppost and other lamppost models, are excluded with the polarization results that we see, because the polarization angle is aligned with the radio jet, so that it must be coming from something that is covering the accretion disk. Okay, so there are other sophisticated geometries. For example, I've been working with Matthew Liska at Georgia Tech, and he's been doing this highly relativistic general relativistic magnetoaerodynamic simulations, and then he was able to see this corona actually forming in real time as blobs of hot material, which could be sort of consistent with some sort of a sandwich-like shape, but it is not covering the entire surface, which is important, because if you cover the entire disk with a corona, that corona is cooled down very, very rapidly with the cold disk photons, and it becomes very short-lived. So these are very recent developments about the shape of the corona in galactic black hole systems. So then, what are the black hole spectral states? When we observe these black holes throughout their outbursts, which take days to weeks to months, we see that their spectral shape changes. And there are basically two so-called states, the main states of black hole systems. And in one case, the emission is dominated by the so-called disk blackbody emission. That means that we have little or no this high energy corona. We have a geometrically thin optically thick accretion disk providing most of the emission. So this is shown with this soft red spectrum. So this is called the soft state, basically, because the emission is coming from low energy photons. But some other time, we find that the emission from the disk is suppressed significantly, but we have this enormous luminosity, not enormous luminosity, but a lot of emission coming from the hard state. Okay. Now, if you look at old textbooks and old articles about these states, sometimes they refer them as high soft state and low hard state. This is actually misleading, because what happened is that because they were only using low energy instruments to differentiate between those states. So if you look at below 10 keV, for example, then really the soft state has a very high luminosity and the hard state has a very low luminosity below 10 keV. But if you look at the entire electromagnetic spectrum, if you look at including the hard X-rays, at certain stages of the hard state, the overall luminosity is actually higher than the so-called high soft state. Because of that, I don't use high soft state or low hard state. I only use hard state and soft state because it better characterizes these different states. Okay, so it's basically whether the disk is the dominant emitter or the Comptonizing corona is the more dominant emitter that differentiate between those two states. All right. So then, since we can differentiate between the soft and hard states, we can come up with a sort of a definition of hardness, basically a ratio of the hard flux to the soft flux. And then we can make a graph of hardness ratio and the overall count rate. Okay, this is called a hardness intensity diagram, HID for short. And whenever you go to a black hole conference, whenever you read an article about a black hole transient, they kind of show this, because this explains the behavior of the outburst and states in one graph in a very beautiful manner. Okay, so the x-axis is the hardness ratio, where you take a hard band and soft band and you take the ratio. Y-axis is the count rate. And what happens in an outburst is that almost all black hole transients follow the same, this counterclockwise pattern, sometimes called the Q pattern, or here it looks like a dolphin with a nicer instrument, dolphin pattern or Q pattern around this hardness intensity diagram. So at the beginning of the outburst, when the luminosity is low, the sources are always in the hard state. They start hard, so you can see hardness ratio is higher. And then as the luminosity increases, the mass accretion rate increases, they go to the so-called an intermediate state. This is where both emission from the accretion disk and emission from the corona are important. So it goes through the so-called hard intermediate state, soft intermediate state, and then this red region is so-called the soft state, where most of the emission is coming from the accretion disk, the geometrically thin disk. And then as the count rate decreases, then it goes to this hard intermediate state again, and then ends the outburst in the hard state. So this is also called a hysteretic pattern. So there is a hysteresis here in the sense that the transition from the hard state to soft state and transition from the soft state to hard state do not happen at the same luminosity level. Okay, it happens at a lower luminosity during the outburst decay. So it doesn't go like this and comes back in the same pattern. It makes a loop. Okay. And now you could see, so this is a little bit details, and I'm not going to go into the details too much, but basically each state has its own X-ray spectral and timing properties. Hard state, they also show these compact radio jets, which I will come back to. It shows timing, very variable emission, fast timing. In the hard intermediate state, we have some quasi-periodic oscillations, which I will talk about. And in the soft intermediate state, which is shown here with only 1 point, in this source, it was very shortly, but some other sources, the soft intermediate state is longer, where we observe so-called a ballistic jet, that the compact jet turns into a very powerful jet, and then the jet dies down. In fact, in the soft state, there is no compact jet. Okay, and in the soft state, the timing signatures, the variability is also suppressed. All right, so these are the main properties of these different spectral states. So let's talk about these jet. Yes. Mm-hmm. So yes. So the typical outburst spans weeks to months. So we're talking about time scales of days. So in fact, each of these observations shown here are taken mostly a day apart. See, so you can kind of see what kind of time scales that we're talking about. And there is a very nice paper by Dunn et al., where he shows all the time scales for state transitions and how long each state lasts. And there's no specific rules that it can stay a lot of time in the hard state and the other state can go faster. There are no rules for that. But we're talking about time scales of days, which is much larger than the dynamical time scales around the black hole, which is less than milliseconds. This is driven by perhaps. So we're going into the discussion of the state transitions, but this must be driven by how the magnetic fields are transported in these accretion disks. So this is the timescales are driven mostly by that. Any other questions? So what is a jet? What is a wind? How do we differentiate between those? As I said, winds are uncollimated outflows, and the winds are observed in the soft state as blue shifted absorption lines. In fact, in my talk on Wednesday, I showed the same graph again. This is the Chandra grating spectrum of 1655. And you could see these absorption lines, which are blue shifted, which means blue shifted means that the matter is coming towards us. And if you measure the speeds, it's quite high, quite large, but it's not as large as the speeds in the jet. Okay, so the winds are high speed, but we're not talking about relativistic speeds. Okay, and in the soft state, especially if you are looking at edge on, so if you're looking through the material, so if you're looking at from the top of the disk, then you don't see that. But if you're looking through the disk, then since the X-rays from the inner part of the accretion disk goes through a lot of this outflowing material, we see these signatures. So these are how we detect winds in X-rays, through blue shifted absorption lines. The jets, on the other hand, we detect mostly in the radio band. So here are two examples. One of them, this is the jet of a black hole system. This is the jet of an AGN, active galactic nuclei. They have sort of similar structure, but of course AGN jets are much, much, much larger. They can sometimes be larger than the entire galaxy. But for the black holes, the stellar black holes, they're much smaller. We talk about light years. So we detect jets with radio telescopes. Since galactic systems are too small, the jets are small, only few of them are resolved. So we have this kind of images from only a few galactic black hole sources. Most of them we see as a blob, but we look at the spectrum to understand the properties of the jet. For the AGN, they're so large that we could look at the details of the jet with our radio telescopes. So these compact jets are observed in the hard state of black holes. Okay. So then it turns out that the behavior of these outflows depend on where we are in the hardness intensity diagram. It turns out that in the hard state, we don't observe these winds, X-ray winds, but we observe compact conical jets in radio. In the hard intermediate state, we observe jets. And during the transition to the soft state, we have these gamma of greater than 2. So we're talking about close to the speed of light. So the jets are extremely fast, okay? And this is the optically thin flares that we observe during the transition to the soft state. Once we are in the soft state, if we observe the source at a higher inclination through the material on top of the disk, we observe X-ray winds, but not jets. So they're kind of X-ray winds and radio jets are sort of observed. When one of them is observed, the other is not observed, basically. Okay. Yes. Mm-hmm. What do you mean by polar index? The gamma is just shows this is the gamma in general relativity. Yeah, it's this gamma is not about the power law index in the X-ray spectrum. It gives you the speed of the jet. 1 divided by square root of 1 minus v square or c square. You can calculate the speed. All right, so how do we understand that these jets are compact, small? Why do I call them compact conical jet? Because, I mean, I told you about this in beginning of the talk, if you look at the spectrum, so in the beginning of the week, you heard talks about the synchrotron spectrum. In fact, the spectrum of a jet, we have the strong magnetic fields in the system, and the electrons gyrating in the magnetic field create this synchrotron radiation from each surface in the jet as you go up from the compact object larger and larger distances away. From each surface, you get this typical synchrotron spectrum. It's very well known, theoretically calculated. And if you add them up from each surface, from the black hole or from the acceleration region up, if you add them up, you get this so-called flat radio spectrum with a break usually happening around near infrared to optical waves. Okay, so this spectrum, broken power law spectrum, is a telltale sign of compact conical jet with a low opening angle. Okay. What about timing? Now, you have heard this term quasi-periodic oscillations. Earlier, we talked about the power spectrum. So let me talk about a little bit more of this without going into detail, because the X-ray timing of black holes could be a lecture of a few hours itself. So I'm just going to condense it down to just one slide here. We have a large scale of different time scales that you observe from black hole systems, especially if you have an instrument like NICER or RxDE, where you have a very good timing resolution. You can get photons at very, very high frequencies. You could characterize photons with millisecond variability. But since your observations are thousands of seconds, you can characterize different time scales from milliseconds all the way to tens of hundreds of seconds. And the way to characterize the variability of an astrophysical object is you take the Fourier transform, basically, and you plot the Fourier amplitudes as a function of frequency. This is called the power density spectrum. It simply tells you at which time scales your system is more variable. Okay, and there are some examples here for the black holes and neutron star systems as well, where the x-axis is the frequency, y-axis here is now the power, the amplitude, square of the Fourier transform, times frequency to bring out the most power in the variability. And you could see that there is variability in all time scales, but there are also peak features. So there are certain frequencies such that the variability is much higher. These peaked features in the power density spectrum are called quasi-periodic oscillations. And here is an example of how you can create such quasi-periodic oscillations. There are different ways of doing that. You could, mathematically, you could merge different sine waves, so you can have pulses, or you can change the frequency of the sine wave a little bit, or you could modulate the amplitude of the wave, or you could have some stochastic injection of pulses in the system. And each of these, so you can see that in this case, this depending on how you do things, you could get these peaked features. Either from the frequency modulation, amplitude modulation, you get similar or different features, basically. And these are then, people try to understand what causes these kind of features in the accretion disk and the surrounding corona of the black hole system. But then, when we look at this power spectra, we see these quasi-periodic oscillations, very powerful. The variability sometimes is dominated by these quasi-periodic oscillations. Is one of the most active paths of studies in black hole systems. What causes these QPOs? And the answer is not given 100% yet. I mean, we don't know we have pretty good ideas, but we cannot pinpoint it to one source yet. And it turns out that there is a relation between these QPOs and these relativistic jets, these optically thin radio flares. It turns out that in a few cases, we only observe the so-called B-type QPOs, shown here, these very powerful oscillations at certain frequencies between 6 and 10 hertz. They only appear when we also see, or they appear very close to the time that we also observe these geometrically thin, very powerful radio flares. So what happens is that this radio flare happens, and then radio dies down. It's sort of the last hurrah for disrupting the jet. It's very powerful optically thin emission coming from the shocks, and then the jet is destroyed after this event. And you could see when the jet is destroyed, when the system goes into soft state, the variability goes down as well. So you can see this better here. Now I show how the power spectra changes with respect to the harness intensity diagram and different states. The power spectrum, we have large continual variability, many frequencies in the hard state. In the hard intermediate state, we have a QPO as well. In the soft intermediate state, by definition, we have this powerful QPOs, but not much in the continuum. And in the soft state, sometimes people say that the disk is rock solid. So the interesting thing here is that hard and hard intermediate state, these are the states where most of the emission is coming from the corona. And the soft state is where most of the emission is coming from the disk. So this tells us that the optically thick, geometrically thin disk is not that variable. And most of the variability is coming from the corona, which then turns out to be very important in understanding the origin of this variability. So whenever we have a corona, whenever we have an optically thin medium, we have high variability, we have jets. Whenever we only have the optically thick disk, then we only have X-rays. No jets, sometimes winds. Okay? How am I doing? All right. Now, this was up to now, I just provided general information about the behavior of black hole systems, transients, and the states and state transitions. I'm just going to talk about my research a little bit. It's going to be a little bit intense, I apologize. But basically, as I said earlier in the talk, we could only understand the big picture by investigating these sources with multi-wavelength observations. So if we can have continuous monitoring with radio telescopes, infrared and optical telescopes, and X-ray telescopes, looking at these sources at the same time, it's the only time we can actually get the whole picture. And there are different methods to do this investigation. Long-term multi-wavelength monitoring, investigating state transition, and studying causal connections. So when does the jet turn on? What happens to the timing properties at that time? What happens to the spectral properties? This is what I do. Causal connections. This might be wrong. Causal. All right, causal. I apologize. Yeah, that's too sexy. Anyhow, so we could fit the spectral energy distributions, because spectral energy distributions go from radio all the way to the gamma rays. And we could do both. There are other ways of studying this, which I don't do, but other groups do. For example, you can look at the correlations between infrared and X-rays, radio and X-rays, or you could do fast timing. Fast timing, I do fast timing in X-rays, but other groups can do fast timing in near infrared, for example, which is very difficult to do. You need 10-meter like telescopes and special equipment to do that. But also provides a wealth of information about these sources. So the results that I'm going to show will be from the SMARTS optical and infrared telescopes, VLA and ATCA radio telescopes, and old RxD data, which keeps on giving. So basically, what is a state transition is abrupt changes in the spectral or timing properties of these sources. Here is an example of this abrupt change. This is the outburst rise of black hole GX310-4. Here, each of these points are from one RxD observation. Here is the RMS variability. Here, X-ray spectral index, when you fit the spectrum with a power law. Lower the spectral index, harder the spectrum. It means that the spectrum is like that. That still stay hard. If the spectrum index is higher, that means that you have less hard X-ray photons compared to soft X-ray photons. So that means that harder spectrum, the higher spectral index means softer spectrum. So here, this is, you can see what goes on here. It's just that in one day, we have this kind of power spectrum to this kind of power spectrum. So it's something changes in a time scale of days. So this is, which I sometimes call the timing transition. Okay, this happens here, for example. So this is one kind of a transition. Here, there's another type of a transition. You could see that the spectral index are moving in a steady pace, and suddenly it increases pace. It gets softer very suddenly. Here, another state transition, right? I mean, you have the near-infrared fluxes and radio fluxes. Up to this point, they're increasing, and then it goes down very quickly. So near-infrared dies down, radio dies down, softens. So it's basically this transition to the soft state, okay, from the hard state. During decay, sort of the reverse occurs. So in the soft state, as I said earlier, there is no fast timing. It's rock as a steady as a rock, the disk, and then something happens in one day or less than one day. We see variability in many time scales. So the corona starts to form, and the variability comes to life here. But the spectral changes occur later, almost 10 days later. We see hardening of the X-ray spectrum, and after it hardens, we see the increase in the near infrared. So once you have these multi-wavelength observations, I think it used to also have, I deleted here, but it also had some couple of radio observations here. Then this is really complicated plot, but it shows three things at the same time. The hardening of the spectral index with black dots. The red points are the infrared rise, and the blue points are radio. So you can see that increase in the radio and increase in the near infrared occurs at similar times, slightly delayed, but similar times. So this tells me that the increase in the near infrared is possibly related to the formation of the jet. But this occurs many days after the start of the softening, the start of the hardening in the black holes. So then I can compare outburst rises and outburst decays. I can look at the radio spectral indexes and come up with this picture. Basically, I can look at the spectral index for the strength of the corona, how powerful the corona is emitting, formation of the geometrically thick medium. I look at near-infrared radio for proxy for jet formation and destruction, and I look at the radio spectral index for jet collimation, because you see this, if it is a flat spectrum, that means it's a compact jet. If it's optically thin, it is extended. Then when I look at many sources, I see this hysteretic behavior, that in the rise, the hardening of the X-ray spectrum and increase in the near-infrared starts at the same time, and they occur concurrently. But in the decay, first spectral index hardens, and then near-infrared rises. So the system waits for the corona to fully form before it can create jets. So that's my basically conclusion. But in the case of outburst rise, contraction of the corona or disappearance of the corona and disappearance of the jet occur at the same time. So this is sort of the idea and the kind of research I do to understand how jets form and die in black holes. Yes. This is outburst. These are the same. So I should have given a little bit more information. These are the same sources in the same outbursts. And the red are the X-ray data, black are the near-infrared data. So it just shows, they both show the same thing, but their behavior is different. So it's another hysteretic behavior. Okay. All right. I think since I was told that I had enough time, so I made most of you to sleep, which is good. So I'm going to stop here. Summary: the long-term multi-wavelength observations is essential to understand the relation between accreting and ejecting components. X-ray timing is important to understand state transitions and characterizing the jet timing behavior. There might be a new hysteretic behavior between near-infrared and radio and X-ray properties. So these are the things that I'm going to say. All right. Any questions? Yes. Well, of course, the main difference is the surface, the neutron stars, either as a surface or the magnetic field stops material coming in further. But I wonder if I have the. No, I don't have it here. There are certain types of neutron stars where you could also construct sort of the harness intensity diagram. They look similar. So the behavior is not that different. The neutron stars are usually softer because they have a lower gravitational well, but sometimes they have emission from the surface and bursts. But other than that, their behavior are similar, especially for certain neutron star systems. That's a different. The jets in neutron star systems sort of have a little bit different behavior. They're not dominated in the heart. So we cannot, I don't know, we cannot really associate the heart state with anything in the neutron stars. But the neutron stars do not show jets when their spectrum is hardest. While in black holes, we see jets when the spectrum is hardest. There are some other reasons for that, which we could discuss later, perhaps. But, I must also go back and read those papers. But there are papers by Simone Migliari which discusses these neutron star jets and their differences. I mean, we see jets in neutron stars as well, but their behavior is a little bit different than black holes. Excellent questions. Any other questions? Yeah, yes. Yeah. So again, very good question because so the physical the there are two ways you could explain these different behaviors. One is related to one is related to jets, how jets behave, and how magnetic fields are transported close to the black hole, which I used in my papers. Is if you look at the spectrum of the jet, there's the flat part, and then there's the optically thin part, and this break is around the near infrared. So the near infrared behavior is tied to the jet emission. Then, and the more compact jet is, the higher the frequency of that break. Okay, so then you could explain these transitions basically by understanding how these poloidal fields that create the jets transported close to the black hole and then diffuses out, which is an extremely difficult problem. And I have a colleague in Georgia Tech working on GRMHD simulations to understand this behavior. So then if you try to explain this behavior with that, when you have the optically thin, geometrically thick corona, that medium makes it easier for the magnetic field to come in and establish close to the black hole that can power these jets. But when the medium is optically thick, it turns out that these magnetic fields, it becomes harder and harder to go inside. So in time, as you go to the soft state, as the disk, optically thick disk comes in, the magnetic flux diffuses out, its strength decreases, and then the jet disappears. So that was sort of my explanation using the magnetic field diffusion. There's another explanation which I didn't go in detail, but there is another theory called hot accretion flow, where it is thought that this near infrared emission is actually coming from cyclotron emission from the non-thermal distribution of electrons in the corona. So I think Yavuz mentioned this one of his slides, that usually we assume that the electrons have this thermal Maxwellian distribution, but if you have a power law distribution of electrons in the corona, then this little bit excess of electrons can produce this near infrared emission. Then this entire sequence may be explained by just simply the accretion disk is coming in and going out, and how the power law of these energetic electrons are changing. So yeah, I don't know if I can answer your question, but this is something that I'm trying to understand and explain as well as part of my papers. Yes. Yeah.
I might be very binary. One of the very interesting example is the signal X3.
Yes.
The
Yes.
Wolf Riot and
Yeah,
the
yeah.
black hole And like in, I think last December, lots of collaboration published the result, and they actually produced an SED from the high state of the binary system, and they detected nearly, up to 4 PeV photons coming from there, and you can see the spectrum is really going like up like this.
Yeah.
And the interpretation was mostly that the electrons might not be the origin because it's super high energies, but still actually at the innermost part of the jet, which is close there, there's a kind of photohadronic interaction. So basically you have the protons accelerated somehow there, and they are interacting with the very dense, let's say, target seeds photon fields there. And from delta resonance, they actually produce photomesons, basically pi zeros, whatever, which decays into gamma rays. And it's a really, it's a 10 sigma detection.
Yeah.
So I think it's not the only one. So recently that, let's say, microquasars becoming a kind of very popular in very high energy, ultra energy.
Yes.
Would like to comment.
I can, well, I didn't go to the very high energies because my knowledge is limited there. But of course, Cygnus X3 is a very, very weird system. This is not, the microquasars I've been talking about, they have a low mass star, but this one is inside another star, basically. It's just that. Cygnus X3 and SS Cygni, another source, which I didn't go into detail. They are really, really weird sources that they have their jet properties. You could see this helical formation of these jets in the radio, these beautiful images, the precessing jets and stuff. So they have yet another type of physics that I am not very, I don't know much, unfortunately. But they're very exciting objects that and with very exciting results in very, very high energies as well. Yeah. Yes. You need a corona to be able to observe the jet, and one. So the two geometries that were suggested, the sombrero or whatever, it's just you have the corona, which covers a large volume, and then the jet stems out of this corona. The other case, the lamppost model, is that the base of the jet is the corona itself. It's just that it is much smaller volume, and it turns out that it doesn't. The lamppost model is really a phenomenological model that it can explain some properties of the X-ray emission. But what is the actual mechanism that launches these jets? We could only have a much better understanding of it, perhaps through these GRMHD simulations. And it has, and they also have their own world. Okay, they're competing groups, they're different results, but these GRMHD simulations usually do not produce this lamppost-like geometries as well. So I think I'm especially hopeful with the group that I've been working with, that we are trying to explain the entire harness intensity diagram using these GRMHD simulations. And if we succeed that, we will be able to answer many questions about what is the geometry of this corona and how the jet forms and how the jet is annihilated. I'm still working on it. So I don't have the exact answer to your question yet, but we might be close. Any other questions?
I have a question on Zoom, actually.
Yes, go ahead.
So I was wondering if there's any cases or any sources that the iron lines detected. For example, they are claiming that the iron lines detected from the brightest camera burst that is observed, detected in 2022.
Okay, so very good question. The reason I didn't talk about iron lines because I didn't have time. There are many, many detections of iron lines. And here's an example here. Iron lines are extremely important to understand the geometry of the accretion disk, especially the optically thick disk. And in fact, I have shown you on Wednesday a couple of spectra that shows these iron lines from new star, for example. There are hundreds of observations of iron lines. They're extremely important because the shape of the iron line is distorted by general relativistic effects. And from these distortions, you can actually find out the inner disk radius, which is also a very important parameter to understand, for example, if the black hole is spinning. I didn't go into these details, but if the black hole is spinning, actually the accretion disk, depending on the direction of the spin, can come closer to the black hole. And there are measurements with the lamppost model. So there's a caveat there. Employing lamppost model, the most of the spins of black holes from the iron line measurements turned out to be very close to one, which is a little bit problematic because spins, all of the spins are close. If all of the spins are close to the maximum spin, it's either that in all of the cases, the system is spinning up somehow. So this is questioned. Again, I have, of course, I'm a little bit biased on that, but this is also coming from the lamppost model. But it has been used. The iron lines are used to understand the geometry of the accretion disk and the spin of the black hole. Extremely important. There are many measurements of it. Short answer to your question.
Okay, thank you.
All right. Yes. Here it is. I don't know if I have it. Yeah. So here is a set of harness intensity diagrams for the low inclination and high inclination systems. And you can see that they are drastically different. So whether the black hole system, the accretion disk is edge on or face on, really changes not only the spectral parameters, it changes the timing parameters, wind behavior as well. So this is a very important type of study. And in fact, when we look at the face on, it turns out that there are some relativistic effects making the spectrum softer. So these HIDs, you can see that they go to lower and lower hardness ratios compared to the high inclination systems that we observe these systems edge on. So it is sort of not only the intrinsic behavior, but the viewing angle also changes the observational properties of black holes. I don't know. I don't know if that is part of the. I don't know if that's part of. I think it does affect because the the iron line the iron line measurements have an extreme high dependence on the inclination. one part of it could be due to that way, but I'm not 100% sure. I have to check. All right. Well, I'm available if you have more questions. Thank you.
So let's